All right, hello, my name is Brittany and welcome back to Probability and Statistics. Today we're going to talk all about discrete random variables and their probability distributions. In other words, we'll cover the PMF and CDF, and we'll see later what those two things stand for. So firstly, let's recall that there are two main types of random variables. There are discrete random variables and continuous ones. And in this video, we're going to focus just on discrete random variables. And let's also recall that discrete random variables have a countable possible number of outcomes that are real numbers. Firstly, let's talk about probability distributions. So a probability distribution of a random variable, let's just call it x, is a way that we can describe probability concerning the possible numerical outcome of this random variable x. And so for a discrete random variable, specifically discrete, let's focus on two main ways that we can express a probability distribution. The first one of the two will be a list, and we'll express this as a list of possible numerical outcomes of random variable x and their respective probabilities. Secondly, another way we can express probability distributions is through a function or a formula. And by doing this, we can calculate the respective probabilities of each possible outcome in a given instance or scenario of the event. And two common ways to write this function or formula is through a PMF, or a probability mass function, or a CDF, in other words, a cumulative distribution function. And let's note that both of these ways are functions that express a probability distribution. Let's talk about the first way that we can express probability as a function, and that'll be our probability mass function. So for a discrete random variable x with possible events x sub 1, x sub 2, x sub 3, on and on, the probability mass function is a function such that these certain things are true. Firstly, that the function of the random variable x is never a negative value. So this is our principle from the axioms of probability about non-negativity. The function will either be equal to or greater than 0. It will never be negative. Secondly, if we take the total probability, in other words, the function for all possible events, and sum them together, this will equal 1. In other words, 100% is defined as our total probability. And this is the sum of all values of our PMF function when you plug in each possible outcome. It'll equal 100% or 1. And let's also note that if any of these characteristics are not true, then our PMF is invalid. Now let's talk about notation, ways that we can denote a probability mass function. We can call this our little f of x function, where we'll notate this function as a little f of our random variable x is equal to the probability of our random variable x being equal to a certain possible outcome of our random variable. And another way that we can express this function is by saying that the probability of x for a given instance of x that lies within the range of x sub 1, x sub 2, all the way to however many possible events of our random variable there are, and 0 for all otherwise. So in other words, outside of this range. All right, now let's talk about an example concerning discrete probability distributions. So let's just say that we have this given distribution, and let's let random variable x represent the number of customers at a coffee shop at 2 p.m. on a Tuesday. And there are a couple things that we can note about this probability distribution. First of all, that our random variable x is a discrete random variable. In other words, it's countably finite, so we can actually count the number of people in the shop. And let's just say that for this discrete value, our random variable x equals 3. And we can say that the statement is true, that at 2 p.m. on Tuesday, for example, there is a 60% chance that exactly 3 customers, no less, no more, exactly 3, are in the shop. All right, so how can we express this probability distribution in two main ways? Well, as we said earlier, we can express it as a list or as a function. So let's start writing out our list. So we can write all the possible values for our discrete random variable as x in the top bar, and we can write their corresponding probabilities from our discrete probability distribution, and we'll literally just copy down the values. And let's also note that the range of our random variable x ranges from 0, 1, 2, 3, 4, 5, 6, all the way to 7, and that this is the set containing these discrete values. Secondly, let's express the same probability distribution in a second way, as a function, and in this case, as we just learned, as a probability mass function, or a PMF. So we know that our PMF function is a little f of x function. We can say that it is equal to the probability of our random variable x being equal to an instance or a possible outcome of the random variable x, so a little x, where these two things are true. Firstly, that the non-negativity principle is true. So we can check that the corresponding probabilities for all the possible discrete random variable values are non-negative, and we see that they are non-negative, so this first statement is true. Secondly, we want to make sure that the total probability statement is true. So we can go back to our list, sum all the values that make up the probabilities for their corresponding discrete random variable values, and see that they do sum to 100%. So we can say that this is a valid PMF. So let me pose a question. Let's say we want to find the probability that on Tuesday at 2 p.m. there are at least 4 people in our coffee shop. So how do we figure this out? So we want to find at least 4. So our random variable can be 4, 5, 6, or 7, where the probability of our random variable is greater than or equal to 4, meaning that there's a minimum of 4 and it can be greater than 4. So we know that the probability of having less than 0 people in the cafe begins at 0%. So if we draw a number line like this, if we write 0, 4, and 7, and we want to find the probability that there are at least 4, so 4, 5, 6, 7, all the way down the number line. And we know that the total probability is 1, or 100%. Therefore, we can say that the probability of our random variable x being greater than or equal to 4 is equal to 1 minus the probability of our random variable x being less than 4. And since we are given a discrete probability distribution, we know the probability of x equals 0, x equals 1, x equals 2, and so on, denoting that there are 0 people in the cafe, exactly 1 person in the cafe, exactly 2 people, and so on. And so we can break down the probability of x being less than 4, saying that is equal to the probability of x equals 0 plus probability of x equals 1 plus so on, all the way to the probability of x equals 3. We can subtract this from 1 and find that this equals 0.23 or 23% chance of there being at least 4 people in the cafe. All right, now let's move on to our other way that we can express a function in terms of a discrete probability distribution, and that'll be a CDF, as we talked about earlier, or in other words, a cumulative distribution function. And this is another formulaic way that we can express a discrete probability distribution for a discrete random variable x, where it has possible events x sub 1, x sub 2, and so on. And we can also say that our cumulative distribution function is a function such that these certain statements are true. Firstly, we also have a non-negativity and total probability interval statement, where we can say that our CDF function will be equal to or greater than 0, or equal to or less than 1. And so it'll lie within this range of being non-negative, but also less than or equal to 1 or 100% our total probability. Secondly, we can also say that our function is a big f of x function where we have a capitalized letter f is equal to our probability of our random variable x being less than or equal to an instance of that random variable x, and that is equal to summing everything from 0 to that random variable x from our probability mass function, and we'll see what that looks like in just a second. And thirdly, we can say that if we have two values x and y, if x is less than or equal to y, then our CDF function f of x is less than or equal to f of y, where x is a possible outcome of the random variable that precedes or is equivalent to y, where y is another possible outcome of the random variable. And let's talk about how we can notate a CDF. So we can call this a big f of x function where our f is a capitalized letter f. We can say that this function is equal to the probability of our random variable x being less than or equal to some instance of our random variable x, some possible outcome, x sub 1, x sub 2, x sub 3, and so on. And to write our solution for what this function equals, we'll have kind of this array of values where we'll start from 0% or 0.0 and it'll go to 100% or 1.0. Our total probability. And for each value on the left side, there will be a corresponding interval representing the possible outcomes for our discrete random variable x. And so on the left side, we'll sum the probabilities from our PMF or probability mass function. And on the right side, we'll have our corresponding intervals representing the possible outcomes. And on the bottom of this row will be our total probability. It'll always be 1.0. All right, so let's talk about an example. Let's go back to our discrete probability distribution example that we just had about the coffee shops and the number of people at 2 p.m. on a Tuesday. And so let's just rewrite real quick our list that we already expressed for our probability distribution. So again, that'll be our little f of x function, or our probability of our random variable x being equal to our possible outcome for that instance, our little x. So I'll just rewrite our list real quick in column form. All right, and now we want to find our cumulative distribution function, our CDF. And so this will be our big f of x function. So what we want to do is sum the probabilities from our PMF function, or our list of our discrete probability distribution values, and sum them across for each discrete random variable value x. So let's begin at 0, and we'll say that the probability up to the point 0, including 0 people being in the cafe, is 0.01. Now let's move on to there being 1 person, and we can say that the probability that there are all the way up to and including just 1 person, that'll be 0.01 plus 0.11 is equal to 0.12. And we'll do this for each random variable value. So for 3, 4, 5, 6, all the way to 7. And naturally, since we know that this is a valid PMF, we know that our total probability is equal to 100% or 1. So when we hit 7, which is the largest number in our range, we should get 1.0 or 100%, in other words, our total probability. And so this isn't yet our answer. We actually have to write this out as a function, as we described earlier. So we can say that our solution is a big f of x. The left side of our function is going to include the summed probabilities, in other words, our accumulation or cumulative probabilities. And on the right side, we'll have these intervals representing the possible outcomes for our random variable x. So let's begin with 0.0. Well, if there's a 0% probability, this occurs before the range even begins. So in other words, our range begins at 0. And so we have to define an interval on the right side occurring before our range begins. In other words, our random variable x will have to be less than 0. For our second row, we'll have the probability that there are exactly 0 people in the cafe, in other words, when our range begins. And so this will be equal to, as we already wrote down, 0.01, and we can define this as the interval including 0, but not yet including 1. So our interval will not yet include 1. And on the third row, we're going to define the exactly 1 person in the cafe. That'll include 1, since it's cumulative to exactly 1 person in the cafe, but it won't yet include 2. So we'll write less than 2. And we'll do this for each interval all the way till we get to the end of our range, which is exactly 7 people in the cafe, and that should be our total probability, or 1.0. And so just a couple quick ways that we can check our work to make sure we're on the right track is that on the last row, it should be our total probability statement. Our random variable x should be greater than or equal to whatever our last value of our range was, and this should be corresponding to the total probability, or 1.0. We can also check that our first row is a 0% probability, which occurs before our range even begins. So let's make sure that our probability begins at 0.0 and that our random variable for our letter x is less than or before our range even begins. And to check any of our statements in between, ranging from 0 to 1.0, we can say that this includes all the summed, or in other words, cumulative probabilities up to 3, but not including 3 yet. So it'll include the accumulation of our random variable x being equal to all the values before in our range, but not including 3. It'll just be up to 3. All right, and just a quick overview. We talked about 2 different ways to express probability distributions for a discrete random variable. And let's note that this is specifically for discrete random variables. Firstly, we talked about expressing this as a list, where we have our random variable x on the top and our probabilities for our random variable x being equal to a specific instance on the bottom. And secondly, we talked about a formula or a function way to express a discrete probability distribution. And that can be firstly as a probability mass function, or shortened down to a PMF. we can remember that this is our little f of x function where we have the probability of x being equal to a certain instance or a certain value, where we're thinking about the probability of our random variable being exactly at or equal to that random variable's value. And secondly, still umbrellaed under the formula or function way to express probability distributions, we talked about cumulative distribution functions, or shortened to a CDF. And on the flip side from a PMF, a CDF is a big f of x function where we have the probability of our random variable x being less than or equal to some value x. And let's note that this is a less than or equal to sign, so it'll be our summed or our cumulative probabilities, including everything from the start of the range to the specified value of x. All right, and that's pretty much all for today. Thank you so much for tuning into another video. I hope you learned something new, and if you have any questions, just leave them down in the comments below and I'll be sure to get back to you. All right, and I will see you next time. Bye.